Yeah, good morning, students. Today we start with a topic called diffusion through a stagnant gas well. Now, in this, what we do is we consider a system as shown in this figure that we have a column. In this column, let's say this is the surface of the column, and over here we have a liquid A. Liquid A. Over here, the surface is Z is equal to Z1. And in the upper part over here, we have a gas, and over here, the surface is Z is equal to Z. Now, what is happening in this system is basically the diffusion is occurring, and liquid A is evaporating into gas B. Liquid A is evaporating into gas B, and we assume that there is some device present over here that is actually what is maintaining this liquid at a level of Z is equal to Z. So it's a sort of a very slow diffusion occurring. It appears to be like the liquid is being maintained at a level Z is equal to Z1. Now at the gas liquid interface, the gas phase concentration is A. At the gas liquid interface, gas phase concentration of A is expressed in terms of mole fraction, that is XA4. Now this is taken to be the gas phase concentration corresponding to the equilibrium with the liquid at the interface. Now that means at the liquid interface there is an equilibrium being maintained between the liquid and the gas phase. Now that is we say that XA1, that is the mole fraction, is basically the vapor phase vapor pressure of A divided by the total pressure. That is total pressure, that is PA vapor phase by capital. Now, provided that both A and B they form an ideal gas mixture. Provided that both A and B forms an ideal gas mixture, and the solubility of gas B in A is negligible, and the solubility of gas B in liquid A is negligible, right? Now at the top of the tube, that means at the Z equal to Z2, at the top of the tube, there's a stream of gas mixture A and B with the concentration XA2, which is flowing past. So at Z equal to Z2, we have the gas phase, the composition of A in gas mixture AB is XA2, which is basically the mole fraction of A at the top. That is the mole fraction of A at Z equal to Z. Now the entire system is assumed to be at constant temperature and constant pressure. That means these are the conditions: constant temperature, constant pressure, and both gas A and B are assumed to be ideal gases. Are assumed to be ideal gases. Now in this evaporation system, what we assume that under steady state, there is like what is happening is everything appears to be stationary. That is, the liquid is being maintained at Z equal to Z1, and the gases B appear to be stationary. Click. So let's derive this thing. Now for this particular system, what we do is we consider a small shell of thickness delta z, and we apply the balance, that is NaZ input and NaZ plus delta z, this thing. Now let me tell you what is NaZ. NaZ is basically the molar flux. NaZ is the molar flux. Now, molar flux for a stationary system, for a relatively stationary coordinates, can be expressed as Na is equal to Xa, that is number of moles of A plus number of moles of P minus C dAB delta X. Now, in this, the first part, the first term is the convective, that is the convective flux, convective part, and this is the molecular part. Yeah. Now, in this, what we do is we apply the balance over here. Now, for this, we also assume that if this is Z1, let's say this is Z2, then the mole fraction, let's say it varies from Z1 is from 1 to 0, and again it's 1 from starting from 1 to 0. So if XA is in this direction, then XB can be in this direction. That means at the topmost surface, where the gas is, the mole fraction of B can be the decreasing one, and at the Z equal to Z1, the mole fraction of A, that is in the liquid gas interface, the mole fraction of A can be the decreasing one, because obviously what is happening is basically the A is diffusing into gas B. So obviously the mole fractions of B at Z equal to 2 will be decreasing, and the mole fraction of A at Z equal to Z1 will also be the decreasing one. Now, for this, for Z axis, so we'll be writing NaZ, that is this thing. So NaZ. Clear? Now, in this case, at Z equal to 1, that is over here, we say that there is no concentration of B present. So NBZ is 0. So what we have is, from this equation, we have NaZ is nothing but minus C dAB delta XA over 1 minus XA, or divergence can be rewritten as dXA by dZ. So this is NaZ which we'll be using. Now what we do is we apply the balance on this shell, and so under steady state, so input minus output plus generation is equal to accumulation. Now under steady state, accumulation part is 0, and obviously there is no generation or no chemical reaction occurring in this, so there is no generation of A or no disappearance of A that is occurring. So it's purely diffusion, that is A is being diffusing into B. So we have input minus output. So let's represent the cross-sectional area as S. So SAZ at Z, that is at the input, minus SNAZ at Z plus delta Z is 0. So if we divide this entire equation by S delta Z, so what we have is NaZ at Z minus NaZ at Z plus delta Z over delta Z equal to 0. We'll take the limits, delta Z approaches 0. So this ends up as dNaZ by dZ equal to 0. And we'll put the expression of NaZ. So we have d by dz of C dAB over 1 minus xa into dxa by dz equal to 0. So we have this. Now, for an if we assume that the system is the mixture, appears to be an ideal gas mixture. So at constant temperature and pressure, C and DAB are almost, constants and independent of each other. So therefore, they can be taken out. So take out that out, and since so what we left is d by dz of 1 over 1 minus xa into dxa by dz equal to. So we're gonna integrate this part. So on integration, what we have is 1 over 1 minus xa into dxa by dz equal to some constant c, and which can further be integrated and can be written as ln 1 minus say equal to c1z plus c2. So this we have. Now let's look at the boundary conditions for this particular thing. Now at z equal to z1, let's say the mole fraction of A is xa1. At z equal to z2, mole fraction xa is xa2. So we'll try to put the boundary conditions over here, get the value of C2, C2. So we have, if we use Z equal to Z1, we have XA equal to XA1. So what we have is minus ln 1 minus XA1 C1 Z1 plus C2. And we use Z equal to Z2, XA equal to XA2. So we have minus ln 1 minus XA2 equal to C1 Z2 plus C2. Now we'll take the difference, so C2 gets cancelled up, and we have ln 1 minus xa2 over 1 minus xa1 equal to C1 Z1 minus Z2. So from here we have the value of the constant C1 as 1 over Z1 minus Z2 into ln 1 minus xa2 over 1 minus xa1, or it can also be written as C1 as 1 over Z1 minus Z2 into ln xb2 by xb1. Yeah. Now we have the value of C1. We'll substitute back in this equation, and let's see what's the value of C2. So if you substitute this back in the main equation, so we have minus ln 1 minus xa equal to, we'll put the value of C1, Z1 minus Z2 over Z into ln xb2 minus xb1 plus C2. Now let's put let's put x equal to, let's use this equation, this boundary condition, the first boundary condition, that is this thing. So xa1 z1. So what we have is C2 is minus ln. Now this can be written as xb1 minus z1 over z1 minus z2 into ln xb2 minus ln xb1. It can be written as this thing. Now this is the value of C2. Now which can further be rearranged. So let's do some modification in C2. So C2 can be written as minus ln xb1 minus, okay, now it can, the bracket is open, so minus z1 over z1 minus z2 ln xb2 plus z1 over z1 minus z2 ln xb1. Now xb1 is taken out common, so it will be z1 over z1 minus z2 minus 1 ln xb1 minus z1 over z1 minus z2 ln xb2. 2. Now this can be rearranged. So this will be Z2 over Z1 minus Z2 ln xb1 minus Z1 over Z1 minus Z2 ln xb2. So let's say this is the value of your C2. Now further, if you look at our main equation was minus ln 1 minus xa is equal to C1 Z plus C2. Now this can also be written as minus ln xb equal to C1 Z plus C2. Now let's substitute the values of C1 and C2 what we have in this main equation. So if upon substituting the values of uh, substituting the values of C1 and C2 in the in this equation. So we have minus ln xp equal to, okay, putting C2, so C1, so we have ln xp2 over xp1 z over z1 z2 plus z2 over z1 minus z2 ln xp1 minus z1 over z1 minus z2 ln xp. Now we have kept all the equation in terms of xp and xp. Now z1 minus z2 is common in this. This can be taken over here. So it's z1 minus z2 ln xp equal to z times ln xb2 over xb1 plus z2 ln xb1 minus z1 ln xb2. Now the minus sign can be adjusted over here. Let's adjust the negative sign over here, so it will be z2 minus z. Now what we do is, in this particular equation we add and subtract z1 ln xb1. We add and subtract z1 ln xb1. So what we have is z2 minus z1 ln xb is equal to z ln xb2 minus z ln xb1 plus z2 ln xb1 minus z1 ln xb2. Now we add this and subtract this, so z1 ln xb1 minus z1 ln xb1. So what we have is, now what we do is we basically combine these two. So we have z2 minus z1 ln xb equal to z2 minus z1. Okay, not this one. So we will take the other one, that is this one, xp1, that is there. Now plus z minus z1 of ln xp2, that is this, and this goes, and what is over here is minus z minus z1 of ln xp1. Now this can be now z2 minus z1. This can be taken on the other side. So z2 minus z1 is common, and we have ln xp minus ln xp1, and z minus z1 is taken out. So we have ln xp2 minus ln xp1. So, or this can be written as z2 minus z1 of ln xp over xp1 equal to z minus z1 ln xp2 by xp1. Further, this can be rearranged. and it can be written as xp over xp1 as xp2 over xp1 raised to power z minus z1 over z2 minus z1. Or it can also be written in terms of now x1 or no xb is 1 minus xa and xb1 1 minus xa1 equal to 1 minus xa2 over 1 minus xa1 raised to power z minus z1 over z2 minus z1. So this is the expression of your molar fractions for a diffusion of a gas through diffusion of a liquid through a stagnant gas. Now further, now if we want to calculate the average values of the average values, so let's say xb average over xb1 is basically from z1 to z2, that is xb over xb1 over dz over the entire volume dz from z1 to z2. So it becomes this thing. Now, this particular term that is in this expression, what we do is z minus z1 over z2 minus z1 can be written as a dimensionless term zeta. So this can also be written as 0 to 1 xb2 over xb1, that is this particular term raised to power zeta over d zeta over d zeta 0 to 1, which is nothing but xb2 by xb1 over ln xb2 over xb1 raised to power zeta integrated from 0 to 1, which comes out to be xb average as xb2 minus xb1 over ln xb2 over xb1. Now that's the value of the average term. Now we all know now this is the average term. Now if we want to find out the rate of mass transfer to this rate of mass being transferred at the liquid gas interface, at the interface how much mass of A has been diffused through B or diffused into B or that has passed through this liquid gas. So what we do is we have NaZ and we'll put Z equal to Z1. Now what is NaZ was minus C dAB over 1 minus XA dXA over dZ. Now we're going to put Z equal to Z1. Now what is dA? This can also be written as minus C dAB over xb1 xa1 xb1 or dxb over dz at z equal to z1. Now we have xb with us. We have the expression of xb. What was xb? xb was xb over xb1 is xb2 over xb1 raised to power z minus z1 over z2 minus z1. Now from this we'll find out dxb over dz and that will purely come out to be over here. So what we have is after differentiating, what I'm getting is I'll write down the directly result. So it is C dAB over Z2 minus Z1 into ln of xp2 minus x over xp1. So this is the number of moles that has been molar flux which has been transferred at the liquid gas interface. Now we have this equation Now, also, let's say this is number 2, and we have somewhere number equation 1. Let me go back and find out where is equation number 1. Um, this one. Yeah. Let's keep this as equation number 1. Now, from equation 1 and from equation 2. So ln xp2 over xp1. So what is that? That is xp2 minus xp1 over x average. So this can also be replaced over here. So from equation 1 and equation 2. So we have NAZ over and Z equal to Z1 is CDAV over Z2 minus Z1 into XB average over XA1 minus XA2. So that can also be written in terms of X. Otherwise, this is the molar flux or mass flux of A that is passing through the interface Z equal to Z1. Or in terms of, if you want to, in terms of XB, so it can be expressed as this thing. So that's it with this topic of concentration distribution of, sorry, diffusion through a stagnant gas. So rest will continue next. Thank you so much.
Thank you, sir.